Thank you so much. I'm very excited to be here, not only because of, thanks to the organizers, but also every one of you in the room, because I already had so many interesting science talks, so thank you very much. Today, I'm going to talk about bedforms. And this is a picture that two people who are sitting here at the front row will recognize, because we've all three been on this dune in Qatar. But I'm not presenting a field work talk today, I'm presenting laboratory work, but this picture is actually motivating my work. If you look carefully, you see a large crescent-shaped dune. We call it a Barken dune. And for non-morphologists, I'll explain later what a Barken dune is. But it's a crescent-shaped dune. It's about half a kilometer across. You see a small car here, just that gives really an idea of the scale. That little dot is a car. And this dune is composed of loose sand on a rocky, hard surface. And if you look carefully here at the top left, you see a much smaller dune. So we have this dune field, loose sand on top of a rocky surface with dunes of different sizes. And today I'm going to tell you about laboratory experiments in my lab. And we're looking at three different problems. The first problem is two different dunes of two different sizes, and they catch up on each other. What happens? The second problem is now we're including fluid and the medium. What kind of effect does that have? And the third problem is I'm putting an object in front of the dune. Is the dune able to overcome that object or not? Those are the three questions that I want to discuss. But I want to take a step back because we find dunes everywhere in our environment. Here we have some kind of roundabout that's completely overtaken by migrating dunes. This is actually in the US. This is close to Lake Michigan. There's a row of houses that are slowly overtaken by marching sand dunes. People have been trying to dig the sand away to no avail. Their house is doomed. Here we have a nice satellite image from Saudi Arabia where you see patterns. So pattern formation is very much an interesting scientific challenge in dune migration as well, and dune behavior. And this is the Golden Gate Bridge in San Francisco. And if you would actually look underneath the water, you would see marching river dunes or bay dunes, which are up to 10 meters high. And they are kind of like migrating along. So dunes happen both in air and in water. And the reason that I'm interested in this is the bigger picture of climate change and desertification. And to kind of put it in perspective, every year 120,000 square kilometers of arable land, which is the state of Mississippi, for the Europeans, that's the size of the country of Ireland, is lost to desertification. So you have dry, dust, sand that's being created. It forms bedforms. They march along, they threaten settlements of people living in these dry areas. And they're very interesting scientific problems that you can look at. For example, the mobility and the speed of the dunes. Can we stabilize dunes, or can we perhaps alter the direction of the dunes? Can we forward project where these dunes are going and when they will arrive at a certain area? And of course, an initial problem is the origin and initiation of dunes, but I'm focusing more on the growth and the pattern formation and the steady state situation. So as I mentioned, there's three problems I wanted to discuss today, but I realized that perhaps only 10 or 20% of you have a background in bedform dynamics. So I want to give you a very quick one-on-one on dune formation, and then look at these three problems that I discussed. So two dunes chasing each other. Now we're bringing in the role of the medium, and lastly, putting an object in front of it. But the key message is that fluid dynamics is key in all of these. So we can't just look at the sediment and the particles. Fluid dynamics is key. So one-on-one, I have three messages for you if you're new to dunes. First of all, think about a little funnel with grains that you're slowly raining down. You form a little heap. Let's say it's a 2D pile. Now I'm blowing from left to right. So I'm creating a unidirectional flow. And then you get the shape of a 2D dune. So on one hand you have an angle of repose, which is usually around 30 degrees. And the other side is a nice kind of S-shaped curve. If you want to know more why this curve is this shape, talk with me later. It becomes very detailed. But we have this asymmetrical dune in 2D. Now if we make it in 3D, which is nature of course, it becomes a bit more complicated. So we have two different axes. First, we have the wind variability. So here we're just blowing from left to right. In 3D, we could either be unidirectional or have a very complex wind regime. And the other dimension is the sand supply. So if we have more sand in our environment, we have different types of dunes. So the first picture you saw was a barken dune. And barken dunes are traveling along they're made of sand, but they're on a rocky bed. And these are barken dunes, but actually the 2D equivalent is for a larger sand supply is actually this cross-section. So what I'm stating here is that the experiments that I'm doing in my lab are 2D, but they're kind of mimicking like the 3D dunes, because you can take a cross-section of kind of the side view, and those are representing our 3D dunes. The second one-on-one message is talking about water and air. And I mean, you may wonder, well, you started with the picture in the desert. In a moment, I'll show you our experiments. They're in water. So can we compare apples and pears? Can we learn something from one and compare it to the other? And if you look at the difference, there are actually quite a lot of differences. You have different sediment transport processes. The density ratio is a factor 3 different. And the time scales and the length scales are very different between bedforms in water and bedforms in air. But importantly, the particle Reynolds number, if you do the calculations, is almost identical. So my statement is that my experiments in the lab, in water, we can extrapolate to things that we observe in the field as well, because of this similarity. And there's some other similarities as well, but the density difference is not the breaking factor, is my statement. The third thing that I want to kind of introduce you to is size of a dune. So the size of the dune, and specifically the migration speed, are connected. So the migration speed is basically the speed that the dune would march along the desert floor, and that's called c. And it depends on the size. And it's opposite to, let's say, soliton waves, if you're familiar with that in your own science field, because larger dunes move slower. There's more sand to recirculate. So the higher the dune, the slower the migration speed. But it's not the only factor. There's also sand flux. Sand flux is related to how strong the forcing is. If the wind blows faster, you have a bigger sand flux. So that is linear, and the height of the dune is inverse. And this has been, and this was a lovely review paper, has been kind of sketched out for both aeolian, which is a jargon word for wind-blown sand, and for aqueous dune, which is a jargon word for water-driven sand dunes. So it's a nice curve which follows this general behavior. So large dunes are slower, small dunes are faster. So now going to our experiments. So this experiment is in Cambridge, and these are the two people that have worked on it in the lab. And this person, for the volcanologists in the room, may recognize him. He's actually a volcanologist. He's now back in New Zealand. This is Paul Jarvis. He set up the experiment, and then Carl has done a lot of the measurements that you will see. So this is the experiment in the lab. It's 2 meters across, so it's a large experiment. It is a rotating channel. So we have about 9 centimeters walls, and it's basically a racetrack, so it goes around. It's on a turntable, it's filled with water and particles. So these red things are particles that are already self-organized in dunes. We're counter-rotating it for specific reasons that I can expand on in a chat later. So we have counter-rotation, water and particles, and this is the experiment that I'll be presenting in the rest of my talk. A few experimental parameters. We have most of the experiments we start initially with a constant bed thickness. We have typical flow velocities and depths which we can adjust. The particles we're using is glass Ballatini because we want to focus on just like smoothness and size. We don't want to worry about shape or other variability. The typical non-dimensionless numbers that we're looking at are particle Reynolds number of 1,000 and a fruit number of 0.2. So we are below subcritical. And we are looking at a driving mechanism at the top with pedals that creates a fluctuation. But over this distance, that fluctuation is kind of evolving into homogeneous turbulence. So we actually get a very uniform driving here at the lower area where our dunes are located. So our dunes are up to 5 or 10 centimeters high. Yes?
How does a fruit number arise in the system?
Sorry, it's a question that... the fruit number is based, I think, on the typical dunes and yeah. So we have a water height and we have a dune height, so that's a length scale, and we get a flow velocity, so you can calculate the fruit number, right?
And what is your density difference? You take the density difference between the water and the particle?
Yes, we do.
But it's not a densimetric fruit number, right? It's just a weight on G. Yeah.
I'm sorry, I'm a little bit caught.
A fruit number for the water, a fruit number for the sediment.
Ah, I see. I think it's the fruit number for the bedform, I think, is how we calculated this. Can I look into it and get back to you, Eckhart? Because I'm not 100% sure. Right, so these are the parameters. So next we can kind of look at the processes that are happening. So we start with a flat layer of sediment, a flat sand sheet. And then over time, there are small ripples that appear. And this goes very, very quickly. So we're kind of conveniently ignoring this regime. And then we get these climbing terraces as an intermediate stage, but they're still connected. And then they are disconnected. So we have a bare surface between dunes of sediment. And this is actually mimicking the picture I showed you at the first slide, where we had discrete dunes on a rocky desert floor. So there's no sediment in between the dunes. So this is the different bedform stages that we're encountering. Now, if you look at the phase space, and let me lead you through this picture. So on the horizontal axis, we have an angle, which is 2 pi, which is our rotating kind of going around. It's periodic, so we go back after 2 pi. So this point at the first measurement is the same as, this point of the second measurement is the same as this point on the first measurement. It just goes around. And then the vertical axis is the time. So in this case, it's 20 minutes. And we initially start with a flat bed, so it's completely flat. Then you get little ripples, they start to interact. You get coarsening, you get collisions, and then in the end you have stable 2D barkans, which are separated between with a bare surface. And I just want to highlight 2 different collisions here. The first one is merging. So we have 2 bedforms coming together and going on as one. And the other interaction is ejection. So 2 bedforms come closer and then they separate again. And the reason that this happens is that small dunes move faster than large dunes. So that's kind of indicated in this picture. A small dune is chasing a large dune. It's faster, so it approaches, and it can have 2 different outcomes because it depends on the height. So it's either merging, so it goes on as one big dune, or it kind of takes a bite out of the front dune. It gains more sediment, becomes bigger, becomes slower, and then the front dune can escape. So this is the fundamental process, but we also mimicked it with numerical simulations with a collaboration with people from IPGP. So that's Clément Narteux and Olivier Rogier. And we try to mimic these 2 processes with a cellular automaton model called Rescal. So first we're looking at coalescence. So we have these 2 dunes that are merging. You have a formation of a plateau. And then as this plateau is being eaten up, it actually goes as one big dune. And the colored sediment is actually merging as well. So that's the coalescence process. And then the second process is the ejection process. if I can start the movie, there we go. It's just two dunes. This is just repeating. So it's approaching each other. There's blue sediment that's being kind of eroded away into this trailing dune. The front dune is able to escape because it's smaller, and it happily moves onwards. So ejection and coalescence. And we try to look at this both experimentally and numerically, and we came up with a phase space to kind of come up with a way that we can predict what the outcome is. And the crux of it is if the chasing dune is fairly small. The chasing dune is fairly small, then it actually merges into one dune. If the two dunes are about the same size, then they actually have this ejection process where they leave again. So this just has been submitted to Earth Surface Dynamics. I want to pause there for a moment because this all is very idealized and very nice, and we validated it with experiments. But I've now just talked about the height of a dune and whether it's able to catch up. But I haven't talked about the medium yet. And if you think about this picture that I showed you early on in the presentation, the dunes are fairly similar size, but they are continuously evolving. And dunes are not ending up as one big dune in the field, right? There are some processes which make this more complicated. And that is the simple answer to that is the medium. So what is the role of the medium? And let's use a little bit of fluid dynamics now. So in this example, I have just two dunes in my system. I have an upstream dune and a downstream dune, and they're the same size, so the same height. So if we look at the specific particle motion, the specific particle motion, my video doesn't want to run. Let me see. It's never good when there we go. Can we see it running? So it's a laminar bed load on the left-hand side, the upstream dune. It's very nicely organized, very layered. It's only a thin layer here close to the surface that's actually engaged in sediment transport. On the right-hand side, however, and hopefully that movie will run, that's downstream dune. You can see a very different character. There are these turbulent sweeps that are coming by, these fluctuations. I'm sorry, the movies don't work very well. Please come to me after the talk and I'll show you the movies properly on my computer. But you get these turbulent sweeps. And that is because this downstream dune is actually feeling the effects of the upstream dune. So it's not only simple geometry, it's also fluid dynamics that's important. So now we can do fun tricks. So we can place two dunes, the same size, in our circular geometry. So here we have dunes which are only an eighth of the rotation apart. And because they're the same height, but this slow dune is actually creating a lot of turbulent fluctuations, this front dune is speeding up. So it's drifting apart to 180 degrees. And they actually end up, in the end, after an hour and a half, at antipodal positions. They're the same size and then the same speed, because this one slowed down because it lost its extra kick. So they're now 180 degrees apart, and dunes like to socially distance. Now we can do different things. Now we can bring in two dunes of different size. So we have a small dune and a big dune, which are 180 degrees apart. Obviously, this big dune creates a lot of turbulence and a lot of fluctuations that will impact the small dune in a different way than the small dune will impact the big dune. So they slowly come together. And if you're just leaving the experiment there, you may think that they're in a perfect equilibrium, that the small dune is fast because it's smaller, but the big dune is as fast because it gets extra kicks from the small dune behind it. But then, fortunately, my student Carl, and I just want to mention that again, he looked further and went further into this investigation and ran the experiment for up to 20 hours. And he noticed a very different dynamic after longer times. This is just 3 hours, but the dunes are kind of drifting apart again. So there's some fast dynamics, where they come together and seem to be in some quasi-equilibrium, and then they move apart again. And this indicates that there's perhaps a different long-term stability. So let me just look at I have about 7 minutes, 8 minutes?
9 altogether.
Yeah, perfect. So the trick here is that we can actually move our experiments faster and faster and see what the effect of turbulence is. And specifically, will the outcome change when we're changing the fluid dynamics above it? So we did that, and we first looked at it from a very mathematical point of view. We simplified the system in a dynamical system with just 2 parameters. The first parameter is the mass ratio between 2 dunes, and the second parameter is the separation distance. And we can change those 2 parameters independently. If we're at point S, here in the middle, the dunes are the same size and the same separation, 180 degrees apart. And now we can perturb one of them, so we can make one a little bit bigger, or perhaps move 2 dunes closer and see what the effect is. And all the details you can read in this PRL, and I don't want to go into the specific details, but the take-home message is that if you increase turbulence, so if you create a faster flow, you have different outcomes of this dynamic. So initially you have fast and then slow dynamics, so the dunes were coming together as we saw and then slowly drifting apart. If we increase the turbulence level, you have a damped oscillator and the dunes kind of start to dance and come together and go apart again, and come together and go apart. And if you really increase the turbulence level, you get an asymmetric attractor, and you get to a state where one dune impacts the other, but the influence is not mutual. So you get actually an asymmetrical outcome, and these are experimental measurements based on a mathematical system. So in the last 5 minutes of my talk, I just want to talk with you about a third, more practical experiment we did, and that's placing an obstacle in the path of a dune. And it has a lot of applications if you think about sand encroachment. So people have been building walls in certain arid areas, and the question I always ask is, well, are you making the problem worse or better if you're placing an object in the flow? Because does it actually capture sand more, and will it stop the dunes, or will it make, you know, a deterioration of your agricultural field worse? And another application is, for example, putting a pipeline in the desert, or a pipeline on the bottom of the seafloor, and seeing where the bedforms are encroaching on it and perhaps passing, what the load is. So there are a lot of explanation, or a lot of applications. And the trick is, will a dune be trapped by an obstacle, or will it be passing? So we looked at different objects, cylinders, squares, ramps, ridges, different sizes of them. And it would have been lovely to look at forces of obstacles as well. So some of my work is using photoelastic grains. So we were playing with the idea to perhaps do that, but it's difficult in water. And I'm happy to talk more about that with you if you're interested. But we're looking at this dynamic evolution. So here we have 6 snapshots. This is our object that we're placing in the path of a dune. You see the dune coming from left to right. The flow is from left to right as well. And you see that the dune is slowly passing over an object. At this point, the object is completely covered by the dune, so the dune will not know that there is an object there. And then at a certain point, most of the sand makes its way over, and it reforms on this side and moves on. And the question is, of course, at which point is an object too large, or, you know, too blunt, or not smooth enough? And we did, I think, something quite creative. We just looked at the flow field. So this is without sediment. So we have our experiment with just the object in there, no sediment at all, and we're looking at the flow field, and we're doing PTV, particle tracking velocimetry measurements of the tracer particles in here. And then my student, Carl, did a modal decomposition. So he looked at the different kind of signatures that are hidden inside of the flow. And based on that, we got a prediction on whether a dune of a certain size is able to pass. And we tested it for 15 different cases, and it worked perfectly. About, I think, 6 or 7 were always passing, and the other ones were trapping, and we got it perfectly predicted without the sediment. So here's a dune approaching a rather large object, and it just stops. And here it just keeps on going. And this is the first pass, this is the second pass. So this object was small enough for the dune to pass along. So I have 3 more slides. I have a conclusion slide, which is today we saw the different interactions between dunes of different sizes, and we can have different interaction outcomes. We saw the turbulent eddies create dune repulsion, where the front dune gets an extra kick because of the turbulence and speeds up. We looked at dynamical analysis of long-term behavior, and we saw that sometimes dunes get in weird equilibria. And we looked at the size and shape of obstacles, and that matters in dune encroachment. I do want to put this slide up there, because dune processes happen in different environments. I mentioned our experiments in water, but they also happen in air, and also in other systems. So Mars, for example, we have dunes of very different shapes. We may have different sediment processes that create different bedforms. So it's just essential to think about this. Another example which I find interesting, and I remember I emailed Michelle when I discovered this a few years ago. These were the 2 dunes that we were, or 2 dunes in the same dune field that we were analyzing in 2013. This is a picture. And then I looked at Google Earth again 3 years later, and this has to do with the upcoming World Cup Soccer Championship. Because if you look carefully, these dunes are gone. And these dunes are like a quarter of a kilometer large. So where did they go? Well, if you look carefully, you see this line. These are 100, 200, 300 trucks lining up to take the sand away for construction of the World Cup soccer stadiums. And they basically just eliminated a lot of these dunes in these dune fields. So society has a big impact on our natural environment as well, which is clear. And I want to finish with the last 30 seconds. I have a short postdoc opportunity available. It's awkward because the postdoc will be based in Cambridge, and I'm not in Cambridge anymore. It's a 9-month postdoc. I'm looking for a candidate with extensive laboratory experience because they will need to work rather independent with me on Zoom for supervision. It's only 9 months, unfortunately, but we will be looking at the effect of the bottom boundary condition on dune migration in our experiment, in both topographies that may be increasing or decreasing or undulating, and also looking at the effect of the roughness here. So if you know of any of your students that are interested in a short secondment, please talk with me. Thank you.
We'll do Tom, and then over there, and then here, and then at the back.
Very intriguing talk, thank you. Can you, with all those nice experiments, I'm wondering, maybe you can comment on what actually, for this kind of unidirectional flow, right? What actually controls the length and the height of the dune in the first place? Because you have small and big dune together. Yeah, thank you.
Yeah, so we did some experiments starting from a layer of sediment, and then we increased the layer sediment. And the interesting thing is our path length is fixed because we only have one diameter. It's about 6.2 meters. So our path length is fixed, but if we increase the volume, we found that we have the same amount of dunes, but the dunes are bigger. So that's the first thing. So the spacing becomes a little bit shorter. It may be an artifact of our limited path length. The other thing that I want to mention is that we have a limited height of our fluid, and if the dunes are becoming too large or the fluid becomes too shallow, they're getting captivated. So the dunes are being shortened, or like truncated is the word.
Decapitated.
Yeah, decapitated, truncated. So it's better to have like a good layer above it.
Thanks for the amazing talk, Nathalie. So I'm asking this question from the point of view of a sand pile models. So when you say like drift speed of a sand dune, what are the role of avalanches in deciding what's the speed of?
Okay.
And if that's the case, then like you'll have a distribution of avalanche sizes, and you won't have a constant speed with which the dune moves, right?
Yes. So how it works in nature is the wind is blowing. There's a pile of sand accumulating at the crest of the dune, or the brink of the dune. And then periodically that pile is failing. I've done some lab experiments 7 years ago or so, 6, 7 years ago, where we looked at the process of, does the avalanche go a long distance, or does it at a certain point stop, and what's the thickness of the avalanche? So perhaps we can talk offline and I can show you that paper.
Ali, for this very interesting talk. I have 2 questions. First one is, so all of this is dealing with supply limited kind of dunes, that is, there is no particles in between the dunes, right?
Yeah.
Have you ever thought of, or do you see that as an interesting question at all, if you had more particles that were there to form the bed so that you have like a continuous sediment bed? Because that's more like the river morphology type of problem, right?
Yeah. So it's basically, if you have this picture, if you remember that. So this middle picture is basically what there we go. This middle picture is what you're referring to. So if I make the initial bed thicker, then these dunes will never separate into like separate unities. They will always stay connected. They will always be these climbing terraces. So the spaces between individual dunes will never erode away. And that is just, bumping up the sediment in the experiment.
Right,
but
would that affect the spacing of the dunes like that Tom was referring to, or anything like that? Anything to this account?
I do think that because of the fluid dynamic processes around the topography here, that the dunes will stay like at a certain maximum distance or minimum distance, if you call it like that, and that there will be a layer underneath.
Right. So it will be essentially a different problem, right?
Yes.
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 Okay.
Very much so. Still an interesting problem.
Okay. Yeah. And then I have a second question on, you showed those numerical simulations. Was there fluid involved at all?
No, it's a cellular automaton model. Again, we can talk offline.
Okay.
But it basically means that you don't mimic individual grains. You mimic cells, which are either moving, stationary, or in a transition between the two kind of like processes.
Okay.
So you're not mimicking. It's not like a coupled CFD DAM model. You're not mimicking flow.
Yeah, I guess we should talk more about this later. Yeah. Thank you.
Thanks very much. Interesting beginning to end. I had a question though about the when you were trapping, you were always trapping a finite size, finite volume, and it looked to me as though it would be hopeless to stop the buildup from eventually just spilling over if you had a regular source of sand. Is that?
So if you have a regular source of sand, you would make a ramp at a certain point. Even if you trap 1, 2, 3, 4 dunes, you would make a ramp. All those dunes would be trapped, and at a certain point, the ramp would be at a slope that you manage for the next dune that comes along to creep up on it.
Yes.
And that is also in that short postdoc we're looking at kind of like the ramp, inclining boundary conditions to see.
So if you can make it steep enough, then you might be able to stop it from coming? Is that?
Yeah, but it's grains, right? So grains,
they'll make their own
this
slope.
intricate process between shear stress and sand flux and topography that
it seems like you might have to have some other process like Qatari trucks coming to take away the sand.
Yes, indeed. But you need at least 300 to 500 trucks. A lot of manpower.
The ejection scenario is really cool. The one that the little one emerge with the large one and then escape.
Yeah.
The escaping dune is on the same size of the merging, or it can be different?
So what you're asking is if, let's say, incoming dune is 2 centimeters, the front dune is 5. After they interact, will they be 5 and 2?
Yeah.
I don't know. I don't know. I don't think so. But we have just looked at incoming areas. We haven't analyzed outgoing areas. Okay. So that is an extra, I never considered this, but that's an extra component that we haven't analyzed. It must be some kind of function of, you know, the incoming boundary conditions. Great question.
Thanks so much, Nathalie. You showed in Dune 101 a formula for the speed, then on sand flux and height.
Yeah.
But then all your experiments showed also influencing the speed is the sense of turbulent fluctuations.
Yeah.
Can you modify your formula based on what you learned?
Yeah, good question. So this is basically the sand flux. And it's, we had 2 weeks ago an excellent talk from Kimberly. We talked a little bit about the sand flux and how it relates to shear stress. But shear stress, obviously, so fluctuations are definitely important and they're critical. And they're not well captured in sediment transport at this moment. It's mainly, you know, average shear stress or average velocity that, you know, Dune experiences. So it's definitely an open question. That's all I can say. Great observation.
Nathalie, very nice talk. I was curious about the emerging dune first, and is there some way that you can tell that it's just like it's the same dune coming out? Do you know what I mean? I mean, I know it's made out of different materials,
but
like,
is your question?
does it look like one dune for a little bit? Like the one dune goes in and then it moves for a little bit and it sort of looks like one dune, and for some reason there's some maybe inhomogeneity that is causing that, or do you really it's still kind of an open question?
So a great question. 2 comments. First of all, in our simulations and in our lab experiments, we've only seen a dune approaching, but never perfectly merging before it takes sand away, before it grows, and then the other one escapes. However, I remember satellite images I looked at in that dune field in Qatar, where we could see, and this is, you know, satellite images, so it happened 20 years before, and it was every year marching along. You could see a tiny dune kind of marching along a very big dune. Yeah. And at the end, it was actually like appearing at the horn again. Yeah. So it may be that we're not capturing that. It may be that we lose, because our experiments are 2D, it may be that is the important ingredient to get that process.
Thanks.
But the postdoc will be partially with Eric Franklin in Brazil, and he has a 3D experiment, and he can see 3D effects.
So then there are another question, these rules of thumb that about dune sort of formation and size in a in a real live river system, and I'm just wondering how I'm not saying that they're right, but I'm just wondering, can you tell, there's sort of phenomenological rules of thumb, as a lot of these are, and I'm wondering if you can tell, if you sort of reproduce that, or if you sort of compare it, or mainly, I could also understand. So when the dune first forms, it's not clear kind of why there's an instability that goes into a dune. Yeah.
So that problem of dune initiation is really difficult. Mm-hmm. We can't do it in our experiment because we can only measure as our experiment is coming by 2 pi later. We're seeing the next process, and the ripple formation, the early initiation process, the linear instability problem happens so fast that we are not capturing the details. So we're conveniently skipping it.
Thank you so much.
Thanks for a great talk. So I was thinking about the scale of the hydrodynamic wake or the turbulent wake compared to the scale of your experiment. And in particular, the finding that these 2 dunes are at the antipode is like that they're maximizing their distance, right? But presumably, if your experiment was a million times as big, I can't see any reason that they would find themselves at the antipode. So it suggests that the turbulent perturbation is actually a very large fraction of the experiment. I was wondering if you had some insight or idea about that.
Let me just, how do you call it, make your question precise. You're talking about turbulent perturbation, but that's the turbulent perturbation from the dune and not from the pedals, right?
Correct.
Yeah. I completely agree. We have one parameter we can play with, and that's the initial volume. So if we have the same system of two, different sized dunes, but we make them each twice as small, then suddenly it sticks less above the ground. So it has a smaller turbulent perturbation. And what we've noticed is if we make the dunes too small, at a certain point, it loses its influence because the path over which the influence extends is running out. Yeah. So yes, it's a finite size problem.
At the end, you showed that object size and shape matters. You motivated that part of the presentation by saying, can we change dune migration? So is there something engineers can now do to slow down sand migration?
Well, digging it away, although it works in Qatar, didn't work in Michigan because I tried to explain that in the second slide, I think. There's a row of 10 houses, and one by one these houses are engulfed by the dune, and they try to dig it away. But if you have a dune and you just dig away a part, you get like the landslides that we've seen earlier today, and it destabilizes further. So you would need to dig away the entire dune, which you only need to be in Qatar to be so crazy. So can you build a wall? Can you block it? I think going back to Jeff's, thank you. Jeff's question. Yes, you can temporarily block it. The first dune may be blocked, the second dune, the third. At a certain point, there will be so much sediment that the dune will be able to overcome that wall. So I think it's a very difficult question.
So let's thank Nathalie again. And we resume at 2 o'clock.